All right, let's do another torque example here. This time is the ladder problem. So I have basically a ladder that is leaning up against a wall here. It has rungs on it. This is not a ramp, but these are rungs here. So you're standing on it, and so you're going to be standing on it. Sure. Some angle theta here. We have friction down here, so mu sub s is equal to 0.5. Mass of the person is 70 kilograms. Mass of the ladder is 10 kilograms. It is no friction up here. Mu sub s equals mu sub k equals 0 up here. So the question is, how far up the ladder can the person go before the ladder starts to slip? Let's give this an angle of 53 degrees. So we start out with, of course, the force diagram. So we have weight acting down on the ladder. Oh, we do need to give a length of the ladder. We'll make it 20 meters long. So there's the weight of the ladder, and then weight of ladder, weight of person, weight of person. So that's the weight. I'm doing F tongue. Normal force. So the person, when you're standing on the ladder, the angle's not that way. The angle actually is up because you're standing on the rung. So this is the normal force on the person, and then normal force on person. This is some distance x here. That's what we're trying to find. We have normal force of ladder vertical, so I'm just call it y sub v. And then we have y sub horizontal this way. There's no tension. And friction, there's definitely friction because the ladder wants to slide out that way, so the friction is acting this way on the ladder, so we'll call this F. There's only one friction we're working with here. We assume that he is perfectly balanced on this ladder, that he is not inclined to slide one way or the other. We care about these two objects here, but let's just go ahead and assume he's in equilibrium. We're looking for that last moment before it starts to slide. So it's not sliding yet. So we're looking for the x value, that maximum value for x, so it won't slide. So he's in equilibrium. So therefore the weight is equal to the normal force here. So I'm just going to go ahead and make that substitution. Now we'll come up with our equations of motion here. So we have, we'll set up our coordinate system, I hat, j hat, and then right-handed coordinate system, k hat. So I have F minus y sub h equals 0. I have y sub v minus weight of ladder minus weight of person equals 0. And then I have my torque equation. So that is based on F equals ma. And now we have torque is equal to I alpha. Now, since it's an equilibrium, we can choose almost any place as our equilibrium spot. There are some places you want to generally pick a place that's going to knock out as much of the math as possible. So there are a couple of logical spots. This would knock out the torque from these two. That would knock out the torque from that one. That would knock out the torque from that one. But that's a little bit tricky because we don't know what that length there is. That's our unknown. We could choose that as the point, and that would knock out torque from this. Or we could also pick that point. These two would have no torque about that point. That would have no torque about that point, but not recommending that because that's an unknown there. And also that spot right there. That has no torque for these two. So we have, we'll throw that one out. That really is not a good choice, but 1, 2, 3, 4 different places. That's going to eliminate 2 of the torques because I have 5 different forces here. And it just makes sense to eliminate as many as we can. For the sake of this, I'm going to choose that as my axis. And so now we need to come up with the equation. So my total torque is equal to the torque from y sub v, which will end up being 0, plus the torque from y sub from the friction, which will also be 0, plus the torque from the weight of the ladder, plus the torque from y sub p, plus the torque from y sub h, and that adds up to 0. We'll get into more detail in just a moment. So now we know doing substitution. So I have friction minus y sub h equals 0. So friction equals the horizontal normal force that way, and that's equal to mu s times, we'll call this mu s, we'll call this 1 and 1 and just leave that as mu s. Mu s times y sub v. I know that value. I don't know yh or yv yet. I know that y sub v is equal to the weight of the ladder plus weight of the person, which is mass of the ladder g plus mass of the person times g, which is mass of the ladder plus mass of the person times g, which we know is 80 kilograms times 9.8 meters per second squared. You know, let's make this not on Earth anymore, but some strange world where g is 10 meters per second squared, just to make the math easier, so make that a 10. And so this is 800 newtons. And therefore, y sub h is equal to 0.5 times, using this formula here, times 800, which is equal to 400 newtons. So I actually know all the forces acting on it. I just don't know where they are acting. So this is where the torque equation comes in. And so shifting this a little bit, bringing back our torque equation right there. This is RV, to simplify it, cross FV plus R friction plus F friction plus R weight of ladder cross F weight of ladder plus R weight of person cross F weight of person plus RH cross force H. That's 0 because R of V is 0. That's 0 because R sub F is 0. This right here is, we've got the diagram there. This R is the distance from here to here. This angle right here is theta. So R, this, again, R sub L is a vector from the pivot point to where the force actually acts. So this right here, RL, is how far over, how far up. I set up to the right is I. So to the right is I, just rewriting what I had before, J and K. So this becomes half the length, so 1/2 the length, times the cosine of theta I hat, plus half the length times the sine of theta j hat, cross my force, which is M ladder G, in downwards, so that's negative j hat, plus RP FP. Well, I don't know where the person is. He's a distance x away, so that's going to be my variable there, plus x cosine of theta I hat, plus x sine of theta j hat, cross the weight of the person, plus the weight of the, cross the weight of the person, which is negative mpg j hat. And then finally, we have the torque from the normal force up here, which is, well, the full length of the ladder, so length cosine theta I hat plus the length sine of theta j hat. It is indeed a vector that's going from the axis of rotation in that direction, in the positive I and positive j direction. Cross, well, the normal force is acting horizontally here, so this is and in the negative I direction, so negative y h j I hat. So this, and that total is equal to 0. So now we can start breaking it down. Now j cross j is 0. So all I really care about are just in this case, I care about that component, I care about that component, and I care about that component, because I hat cross I hat is 0, j hat cross j hat is 0 in both of those cases. So this simplifies down into 1/2 L mg cosine theta negative, and then I hat cross j hat, plus this bit right here, which is negative mpg x sine theta. Try that again. Multiplying these right here. So negative x mpg cosine theta I hat cross j hat. And then the last bit, this is the part I care about. So minus yl sine theta j hat cross I hat equals 0. I cross j is k. That's a classic right-hand coordinate system. So this is negative 1/2 L mg cosine theta k hat minus, again, another k hat, x mpg cosine theta k hat minus, and then over here, this is equal to negative k hat. So plus yl sine theta k hat equals 0. I can basically factor the k hat out. I'm left with negative 1/2 L mg cosine theta minus x mpg cosine theta plus yl sine theta equals 0. And that's the math problem I'm dealing with here. We know all the numbers except for x. So we do a little plug and chug here. So L is equal to 20 meters. M, this is mass of the ladder. I should actually throw the mass of the ladder in there. Yeah, it's there. Mass of the ladder is 10 kilograms. G is 10 meters per second squared. And cosine of theta made at 53 degrees. Cosine is 0.6. And so if we just do that step by step, assuming I don't make a careless error here. So I have 0.5. 20 times 10 times 10 times 0.6 times. So this is negative 600. This right here, I don't know x, but I can know the rest of it. So the mass of the person, that's 70 times g, which is 10, times the cosine, which is 0.6. So 700.6, so it should be 420. So minus 420x. And then over here, this y, this is the horizontal y. And the horizontal y we calculated already. That's equal to the friction, so that's equal to 400. So this is 400 times 0.8, which is 320. So the math problem we were working with here is negative 600 plus 320. So that's 280, so negative 280 minus 420x equals 0. And so x ends up being the negative number here. So we got 280 divided by negative 420. So 280, 420 divided by, and we get, something we'll just round off, make it less satanic. So negative 0.7 meters. Now, what does that mean? Now, there might be a careless error in here. You can double check that. But the negative answer, what does it mean? Well, negative answer means that ladder's, when I'm standing over here, it's going to start to slide. That means that this ladder will start to slide before I even step on it. I think there's a careless error in there because that doesn't seem right. If I'd gotten a value greater than 20 meters, that means that it would never slide. And if I'd gotten some between 0 and 20 meters, that means that, well, that's where I would be standing. The negative answer, assuming that that is correct, is that it is that the ladder slides before I even step on it. I'm going to do a pause and see if I can find the mistake. Otherwise, that's it. All right, so I did find the error here. I lost my L here, so there should be length, the L right there. So This 320 will end up being 6,000, 6,400. So let's see, L was 20 times 400 times 0.8, which is the sine of 50 degrees, so 6,400. So we end up with 6,600 minus. So we end up with 5,800 minus 420x. So x is equal to 5,800 divided by 420. So 420 divided by, and we end up with 13.8 meters. There we go. That's making more sense. So when we get up to, that whole thing's 20 meters, and that's at the halfway point. So when we get to actually somewhere around there, somewhere around here, that's when the ladder will start to slip. And so that is the solution. Loads of places make careless errors. I understand if they were made. Anyway, that's the end of that video.